Day 47, page 1070, problem 36. All right, here's a nice problem. Ties a lot of things together. I have a little diagram here. Basically what's happening is I have photons coming in, and if it's lucky it hits an electron and it releases the electron and gives it its maximum total energy so that the electron is emitted with a fair amount of kinetic energy, and it's going to start flying across to the right. However, if you apply a voltage to two parallel plates, such that the right plate here that I have indicated is negative, the electron is going to be slowed down and stopped. And the idea here is, it says the stopping potential is 4 volts. That means that electron just barely makes it, or actually doesn't, it makes it almost to the very surface of that negative plate, stops, and then gets shot back towards the positive plate, because then it naturally wants to go in that direction. So that's called the stopping potential. It's just enough voltage to not allow the electron to get to that plate on the right-hand side. Because if it has enough velocity, it can get there. Even if it doesn't want to go there, it can get there. So there's a lot of things we got to think about. I'm going to sort of start now backwards. We have this idea right down here, the wavelength equation, the Broglie wavelength, because it says something about momentum in this problem. I can look at the given, the momentum, and I can figure out the wavelength of the original incoming photon. The reason why I want that is because if I know the wavelength of that photon, well, let's rearrange that equation over there that I've circled in blue. Whoops. That is, oh no, I don't have to rearrange it. I can just calculate lambda, and I'll do this in standard units. That'd be 6.63 times 10 to the negative 34th divided by the momentum given, 3.5 times 10 to the negative 27th. Check the units, which they're standard. That'll give me the wavelength of the incoming photon. Using that, I can get the frequency like we did in the previous two problems. That is using V equals lambda F. So now that I know the velocity is 3 times 10 to the 8th, that's a photon. That's 3 times 10 to the 8th, sorry about that. Equals the wavelength you just calculated, finding the frequency now of that photon. Once you have the frequency of that photon, you can get the energy of that photon, which will then be plugged into the equation, so you'll know this. All right, that's the same progression we did in the previous two problems. Now, to get the kinetic energy maximum, that's related to the stopping potential. I'm going to go to the top up here and write a few things down. For example, delta V, the potential difference between two parallel plates, equals delta U over Q. So in other words, as that electron has kinetic energy and it's slowed down, it's kind of like throwing a ball into the air, it's just barely going to make it to that negative plate. It actually doesn't quite make it there. It makes it to the very basic surface of that plate, and it will have a lot of potential energy. But as it flies back the other way, it will gain the kinetic energy that it once had when it was released from the metal. By the way, that black thing I have there is supposed to be the metal that we're dealing with. I'm not sure what metal it is. It doesn't tell us. Or does it tell us what metal it is? Doesn't tell us. But that was supposed to be my metal surface that the photoelectrons are being emitted from. But bottom line here is I know that delta V is 4 volts, 4 joules per coulomb. So in other words, if I rearrange the equation once again, I get delta, let me go back to red. Delta U, the change in potential energy, will be delta V times Q. And this is an electron. So delta U is going to be the 4 joules per coulomb. That's my potential difference. I like joules per coulomb instead of volts. 4 joules per coulomb times 1.60 times 10 to the negative 19th coulombs. That's a 19 there. Coulombs. That'll give me the change in potential energy of the electron. Oh, come on. Delta U is going to be that value. Well, that will also be the delta KE, or in other words, the KE max. So that will be the KE max. And if you have that in joules, and you have the energy of the photon in joules. Let's go back over here now. We just figured out the Ke max, which was related to what I did over there way on the right, this Ke max right here. That just gives me then now the threshold, or the work function. So that's the energy associated with the threshold. The work function would then be, if you had an incoming photon with the energy that matched the work function, that would be the threshold photon, and it has an associated frequency and wavelength. So you could talk about the threshold frequency or the threshold wavelength of that particular photon. So what you'll be doing is plugging in your E and your Ke max, solving for the work function, and now we would associate that with a threshold. So now we would now switch to a new photon that has that energy. In other words, we're going to look at E equals HF for threshold conditions. So that's all associated with threshold conditions. So now we wouldn't have photoemission, or we would barely have photoemission. In other words, take your work function, plug in for E. That would be the condition where there would be no kinetic energy of an emitted electron, or basically an electron that's emitted without any kinetic energy. That's threshold. And then you plug that in and watch your, whether joules or electron volts, and pick your appropriate Planck's constant there. And you could calculate the frequency associated with the threshold photon, which would barely get the electrons loose from whatever metal surface you're dealing with here. You could also figure out the threshold wavelength then using V equals lambda F for that particular photon.